evaluating a function, it's very straightforward. Take part A, we evaluate this function at 1. So we have 1/2 times 1 to be squared times I minus, if t is equal to 1, then we have 1 minus 1j. And so the j component goes out to be 0, so all you have is just 1/2 I. Part B, r at 0 is the 1/2 times the 0 squared I minus 0 minus 1j. So that just gives us j. Part C, r of s plus 1. This is 1/2 times s plus 1 to be squared I minus s plus 1 minus 1j. Simplify that if you want to. I think that first component is fine by itself. You probably just leave that just the way it is. That second one, we can do some simplification on that, and so that would be just minus sj. Part D, r of 2 plus delta t minus r of 2. So that's equal to 1/2 2 plus delta t to be squared I minus here we're still looking at the r of 2 plus delta t first. So this is that function is defined with the I and the jth component. So this is minus t, which is 2 plus delta t j, and then all of that minus r evaluated at 2. So we plug in the 2 there for t squared I minus 2 minus 1 j. Now we try to clean that up. So that first guy, we have to break all that down. So this is 4 plus 4 delta t plus delta t squared I minus 2 plus delta t j, and then this is minus 2I minus j. I'm going to collect the like terms together, get the i's together, and get the j's together. So the I components are here, then the jth components are there. So if we write all that together, notice that this is minus 2 on this I here. We've got to run that 1/2 through there and do some simplification and do some moving. Let me move down this part. So let's do just a little more simplification. 1/2 ran through there as 2 plus 2 delta t plus 1/2 delta t squared. I'm going to bring in this minus 2, all that I, and then minus 2 plus delta t for the j, and then minus 1 for that j. And so we have left 2 delta t plus 1/2 delta t squared. This is all times I. And then this is now minus parentheses 2 minus 1 is 1 plus delta t, and that's j. In exercise 17 and 18, find the dot product of RT and UT is the result of vector valued function. Then it says explain. Well, the dot product is a scalar. So no, it's not a vector valued function. Just becomes a scalar or a function, if you will. So let's see R of t dot with U of t. So this is 3t minus 1i plus 1/4 t to the third j plus 4k. This is the dot product with the u of t. So this is t squared I minus 8j plus t to the third k. So we get the like components together. So the dot product here becomes the 3t minus 1 times the t squared. We get the I components together. And then this is plus 1/4 t to the third times the negative 8. Those are the jth components together, plus the kth components, 4 times t to the third. And so here we're just left with simplification. So we have 3t to the third minus t squared minus 2t to the third plus 4t to the third. So this is 3t squared minus 2t squared. So that gives us 1t squared, t cubed, excuse me, 3t cubed minus 2t cubed plus 4t cubed is 5t cubed, and then just minus t squared. Well, let's look further. Sketch the curve represented by the vector valued function and give the orientation of the curve. So if you take something like 23, This is t over 4I plus t minus 1j. So we want to convert to rectangular coordinates. T is equal to, x is equal to t over 4, excuse me, and y is equal to t minus 1. And so if this be the case, we say that this implies that 4x is equal to t. From the first, and then we substitute the value of t into the second function. So we have y is equal to t minus 1, where t is 4x minus 1. So we get just a linear graph. So if that be the case, then what we will do is we'll look at t and we'll look at the value of x and the value of y. T starts at 0 and we count from such. So if t is 0, then obviously x is 0. If t is 0, y is negative 1. We can also get the same inference over there as well. If t is 1, then x is 1/4, and if t is 1, y is 0. If t is equal to 2, then x is equal to 1/2. Again, t is 2, y is equal to 1. And let's just get one that give us just some smooth points. If t is equal to 4, x is equal to 1, and y is equal to 3. So now we're able to graph this in the xy plane. So when x is equal to 0, y is equal to negative 1. And when x is equal to 1, y is equal to 3. Now the orientation, that is the direction of the path as it moves along the straight line, if you look at that, when t is 0, we were starting out here at 0, negative 1 for the point, and then we kind of moved upward. So this is the direction of the orientation. Let's look at another one. Consider number 27. So r of theta is equal to cosine theta I plus 3 sine theta j. So what we have here is that x is equal to cosine theta and y is equal to 3 sine theta. Now we know that cosine square theta plus sine square theta is equal to 1. So we have the cosine isolated, but for the next one we have that sine theta is equal to y over 3. So to produce cosine square theta plus sine square theta equal to 1, then we simply just replace the cosine with x and replace the sine with y over 3. And so what that gives us, cosine squared would be x squared plus, and sine squared would be y over 3 squared, or y squared over 9 is equal to 1. Let's see if I can make that y a little bit better. Now, see if I can blow this up so you can see it. This is x squared over 1. I'm going to write that as 1 squared. Make that 9 3 squared. That's where it came from, right? So here we have an ellipse. Now if we think about its graph, so the elongation of the ellipse is with respect to the y-axis, because we have the pole positions there pulling 1, 2, 3 plus or minus 3. So you know that A is plus or minus 1 and B is plus or minus 3. So we have this ellipse doing that. Now the question is on the direction. So we have theta and then x and y. So theta is 0, so cosine of 0 is 1 for x, and when theta is 0, sine of 0 is 0. When theta is equal to pi over 2, cosine of pi over 2 is 0, and sine of pi over 2 is 1 times 3. We get 3. When theta is equal to pi, cosine of pi is -1, and sine of pi is 0. So let's see if we can map that on this ellipse. So we have x, it's 1, y is 0. So we're there. And then we move to 0, 3. We're here. And then we move to -1, 0. So it's going around in this fashion. So that's the orientation, right? Now next, let's compute the limit. Very straightforward from before, from calculus 1. So this limit, we evaluate t at pi. So this becomes pi I plus evaluate cosine at pi. That's a -1. I just put here -1j, and then sine of pi is 0, so plus 0k. Now that's not okay. Okay, it's 0 times the kth component, so this is pi I minus j. Well, moving on. What about number 65? So we evaluate each of these terms. We check for continuity. You don't have continuity here for that kth component because cosine of 0 is 1, so 1 minus 1 is 0 divided by 0. So we have an indeterminate form. That's a definition, by the way, of a theorem, if you will, from calculus 1. But if you forget that, we can use L'Hopital's rule to compute that. The first two you can just plug in because they are continuous, so the limit exists at the function value. And so that first component here is 0 squared times I, so it's just 0I. And then this is 0 times 3, so plus 0 times 3j. Then I'm going to write this as plus the limit. I'm going to leave it there as t goes to 0 of 1 minus cosine t all over t. Okay. Now, since it's indeterminate form of 0 over 0, we can do one of three things. You can factor if factoring is possible. You can rationalize if rationalization is possible. Neither two are possible here. And then thirdly, you can use L'Hopital's rule. We'll use L'Hopital's rule. Or if you remember the theorem from Calculus 1, just use that, and you'll get the value for 1 for that particular limit. Well, let's see. So these two, the I and the j components, are 0. This is still number 65. So here we got 0, and this one is 0. So all we're doing is computing that kth component. So L'Hopital's rule said that if we have some indeterminate form, then you can evaluate the numerator, look at its derivative divided by the derivative of the denominator. So the derivative of the numerator, the derivative of 1 is 0. The derivative of cosine is negative sine times a negative, so we get positive sine. T. And this is divided by 1 now. The derivative of t is 1. This is times k. Oh, I told you that the result would be 1. I was thinking about as t approached a different value. Wasn't thinking about t approaching 0, but t is going to 0. So sine of 0 is 0. So we get 0 for number 65. What about continuity? Lastly, in exercise 69 and beyond, I just only have 2 problems here to consider. Determine the intervals on which the vector value function is continuous. So if you think about 69, the only hiccup that we have is in our denominator, and that is that t cannot equal to 0. So for number 69, r of t is continuous for all t such that t is not equal to 0. Now, a different way you can write that, you can say that we have the set of all t. Obviously, even for the first one, t is real, such that negative infinity t goes, that is, t would go from negative infinity to 0, open, union with 0 to positive infinity. Or you can just say t is not equal to 0. Okay, number 70. Here, this, back in 69, for that ith component, t can be anything, right? And you get values that exist. For number 70, for the ith component, t has to be positive. So the first thing we note is that t must be greater than or equal to 0. Now for that second component, for the jth component, t minus 1 has to be greater than or equal to 0. Now this implies that t has to be greater than or equal to 1. T greater than or equal to 1 is the intersection of these two mathematical statements. Right? It's the lesser of the two. And so the intersection has to include everything. Right? If two sets intersect, then that's their commonality. So here you have the first part and the second part, but they have it's the common intersection of t being greater than equal to 1, not 0. Hasty generalization. So here the so-called continuity is the interval of all t, that's a real number, such that t goes from 1 to infinity, or you can say for all t real such that t is greater than or equal to 1. However you're to write it, they all say the same. I guess I can make that look a little bit better, not like Charlie Brown wrote it. I like Charlie Brown. Maybe it's Charlie Brown. Thank you.